Hello, today I'm looking at M3 International A-Level, May 2016. I'm looking at question 3. And here we have particle P of mass m is attached to one end of a light elastic string. Natural length L, modulus 4 mg. So I will begin by making a note of that. So the natural length is L and lambda is 4 mg. The other end of the string is attached to a fixed point O on a rough horizontal plane, rough meaning friction. So here I've got this O and then I've got this particle attached to the other end of the string somewhere. The coefficient of friction between P and the plane is 2/5, so mu is 2/5. And the particle is held at a point A on the plane, so I'll call this point A, where OA is 5/4L. Well, if the natural length is L and it's held here, then this is longer than L by L/4. So I can just do this minus this to get that difference. It's released from rest, so here there is no kinetic energy. And the particle comes to rest at the point B. Show that OB is less than L. Okay, so what is going to happen is when it's here, there's no kinetic energy. There's some elastic potential energy. And up to this point here, there will be some elastic potential energy. But when it gets to this point here where you get the natural length, then the elastic potential energy will be 0. And because this is a string and not a spring, then once it moves over here, there's no change in the elastic potential energy as it moves. So then I can look at, well, where does that energy go? Well, it comes to rest at this point B, which they're saying is over here somewhere. So let's just pretend B is here. And it's at rest here as well. So what I can do is look at the elastic potential energy, look at how that energy would get used up. Well, it would get used up in doing work done against the friction, and compare those two amounts and then see if the speed would be 0 or not when it gets to this point here. So in other words, is it going to move a little bit further or not? So if I look at the elastic potential energy at A, then the formula is lambda times the extension squared over 2 times the natural length. So in this case, it's going to be lambda, which is 4 mg, divided by 2 times the natural length, and the natural length is L, so I've just got 2L there, times by the extension squared, and so that is going to be times by L/4 times L/4. So I can see that an L is going to cancel, a 4 is going to cancel, and I'll end up with mgl over 8. If I look at the work done against friction, then here I need to first of all figure out what the frictional force is. Well, I know that R is going to equal mg, because the mass was m, so the weight is mg. So the normal reaction force up will equal the weight acting down, and therefore the frictional force will equal the value of R times mu. So I've got 2/5 mg, so that's the value of friction, multiplied by the distance moved. And so I know from here to here the distance moved is going to be L/4. And so here we're talking about from A to when the string no longer extended. Okay, so this will give me, that will cancel with that and give me a 2 on the bottom. So here I get mgl over 10. So the work done against friction is smaller than the elastic potential energy. So that means that when it is at this point here, it still has, there's still some of this elastic potential energy to get kind of used up. So it would move a bit further than this point. So I could say something like, since mgl over 8 is bigger than mgl over 10, then what can I say? Then some of the elastic potential energy still can convert to kinetic energy once the length of the once the distance moved is L over 4. So in other words, it's going to keep moving beyond this point, and so it's going to move over here. So I can say, therefore, OB is less than L. Okay, so that's for the first 4 marks. Then it asks me to find this distance OB. So I can just say, well, the energy that it has at that point is the difference between these two. So mgl over 8 minus mgl over 10 will give you the energy that you've got left at that point so this is when x equals 0. So that's the energy that you've kind of got left at that point. In that moment, it is kinetic energy because it's moving, but what we want to see is how far it moves beyond that point to here. And so that kinetic energy that you've got there is going to turn into work done against friction. So the work done against friction is, I can look back at this expression that I've got here. So the work done against friction is the frictional force, which is 2/5 mg, times by the distance moved, so I'll call this d. And I can see that I've got mg everywhere. And if I do 1/8 take away 1/10, then I get 1/40. So I've got here 1 over 40. To get d, I can times by 5 and divide by 2. And that will cancel with that and give me 8. And so I'll get that d is, sorry, there's an L there, is L over 16. Okay, so that is the distance that it moved from when x is 0. And what do they actually want? They want the distance OB. So O is here, B is where it comes to stop. We were looking here, so that distance is L from there to there. We just work out this distance here, D, is L over 16. Therefore, OB is going to be L minus D, which will give me 15L over 16. Okay, so that part of the question is worth 3 marks. I hope you found that solution helpful. Good luck with your studies.